Today I'll be presenting a paper titled Improving Robotic Generalist Policies via Flow Reversal Steering. This paper was released very recently, I think in this month. So it is only an archive preprint by some authors from Stanford and Berkeley. And here are some links to the archive and project page. And I do recommend to check out the project page because there are a lot of interactive visualizations to be able to understand this paper. So a bit of an introduction for this paper is that, as you may know, robotic foundation models are trained on large diverse data sets, and they are very general policies. And these models contain very rich behavioral priors over useful skills, but they may still fail on new tasks that is out of distribution. So how can we effectively access and steer these priors to be able to solve new tasks, for example, at test time? So what's recently been a trend is doing something called policy steering, which means to guide a pre-trained policy's action generation towards task relevant behaviors. And this is done without retraining the full model. So basically at test time, you steer the policy. And specifically for diffusion and flow policies, such as VLAs, the steering usually modifies the denoising process. Or maybe you also choose the input noises that may also produce better actions. But currently, there are some challenges with policy steering. One is that, for example, finding good noises are very hard to find. And usually people, the previous work referred to methods either, for example, trial and error through reinforcement learning, such as DSLR from Call 2025. But these methods are usually very expensive and very time consuming to implement. So the motivation behind this paper is that how can we use instead semantic knowledge to be able to steer generalist policies so that it's able to sample reasonable actions for new tasks. And this is something they call flow reversal steering, or FRS. And the key idea here is we try to map course reference actions to their original noise by passing them through flow policies in reverse. And I'll explain a bit more about this, but what this allows is one is zero-shot steering with only semantic guidance, and also allows you to be able to efficiently adapt through noise-based BC and also RL. So as mentioned, the key idea is to use a coarse or a rough reference action to then find a corresponding latent noise by reversing the flow in reverse. And then once you find that noise, you then denoise it to produce a refined distribution action from the generalist policy. So for example, for a standard flow denoising, you might start with a random noise and then you try to sample some actions from there. While in FRS, you start from an action, so a reference action, they call it, and then you reverse it to noise, which is allowed in flow matching because of the deterministic nature of it, and then you denoise it again to a nearby in distribution action mode. So for flow reversal steering, there's essentially 3 stages. One is the course guidance, where a human or VLM needs to provide a rough reference action. And then second is the flow reversal. So once you have this reference action, you need to map it to a noise and then you denoise it again to get a refined action. And then finally, we can talk about how can we actually use this flow reversal to improve policies. And this can be either through zero-shot execution, through behavior cloning, or reinforcement learning, RL. So the first stage is called course guidance. So oftentimes, generalist policies like 0.5, when you try to command them directly to a new task, it often fails. And the key for FRS is they use a reasoner, and this could be a VLM or a human, to try to steer the policy towards the correct behavior in its prior. So for example, in this figure on the left, you might have, for example, the robot doing an action, and then the reasoner, which is a human or a VLM, tries to output a simple directional command. For example, the robot might should move to the right faster, or maybe some kind of direction. And then you convert this into a rough steering action chunk. So you convert this into a very rough action chunk, which when you try to execute this action chunk directly, it will usually fail. But the key insight here is it's very useful as a reference for steering, right? So so essentially, using human or VLM, you have this kind of high-level guidance called reference action. So then now, once you have this reference action, how do you actually use it for flow reversal or denoising? So the key part here is that flow denoising is deterministic. So that means a flow can be reversed to get the original noise behind any kind of action, and then re-denoise it to project it into the actual generalist prior distribution. So once you have this course reference action, so for example, as mentioned, move right, for example, or move straight right. And then you pass this through the full policy to recover its actual original latent noise. And then this noise is then, so this noise is, and then the noise again forward into a refined action. And the key here is that the final denoised action will be roughly consistent with the reference action, but it will be more fine-grained and in distribution to the original generalist distribution. So so this is the key idea behind flow reversal, where you have an action and then you find noise behind it, you denoise it to get a better action. So that's essentially what the method is. So finally, the most important part is once we have this method that can turn a course action into a useful action, how can we actually improve policies using it? So there's three methods. One is zero shot, where we just directly execute this kind of flow steering. A second one is we do supervised learning on the noise itself. So what this means is that we train a small noise policy that treats the noise that is recovered as the targets for the policy. And finally is we try to bootstrap RL. So using FRS, we can have a prior for RL, and this is supposed to make RL more efficient. So they combine the SLRL with FRS. So first, I think is the most simple one is zero-shot online steering. So here the key idea is we just use the directly FRS without additional training. So what happens here is at every step, you query a reasoner, which was a human or VLM. You ask them for a course reference action, and then you pass it through the flow reversal to find the corresponding noise, and then you denoise the noise to get the final action. So it's very simple, just applying it directly. But one limitation is that you need to always ask the reasoner, be it a human or a VLM, every time you do this. So it's very expensive, especially if you ask a human to do this, right? So, but I think the results on here is when you compare it to maybe a base policy that has no steering, or maybe also a VLM that executes direct actions, zero-shot FRS already actually beats base VLE at Libero benchmark. And it shows that it also beats direct VLM execution, which means that the flow reversal, it refines the original course action into more refined action rather than just reconstructing the same action. So this shows that it actually improves upon the action. And going into the second method, so the first method, as mentioned, we need to always ask the reasoner at every step, every time, so it's very expensive. But here, the key idea is instead of applying FRS directly, we can train a small policy, we can distill a small policy to identify good noise from FRS. So for example, and this is called diffusion steering via behavior cloning. And how it works is essentially, as mentioned, one, you have a small noise policy that is trained on a pair of observation and noises, and you want it to imitate the noises that was recovered from FRS. So this way, it imitates the good noises instead of maybe random or bad noises. And this can be done from either successful rollouts or from some offline demonstration also. And at test time, you the noise policy will output the noise, and then you will have the base policy denoise that noise into an action. And why this works is that because in out of distribution states where usually the base policy always has compounding error, the generalist here will still map noise to a reasonable action compared to where a standard BC might fail. But one limitation is that because this is essentially distillation, it can never surpass the original FRS, and the reconstruction is quite approximate also. But when you actually try here to compare quantitatively, at the very least, the diffusion steering via behavior cloning actually somewhat matches the zero-shot FRS, showing that this distillation actually works pretty well, and actually already beats the base VLA, which is also what we want here for the policy. And it's also very highly efficient because you only need a small sample of rollouts to actually train this small noise policy. And then also it's under 1 minute to train with just 1 gigabytes of GPU. And finally, the next idea is to use FRS to bootstrap reinforcement learning. So what this does is that it makes the trial and error search in RL much more efficient. So what they do is just they pre-fill the replay buffer of the original diffusion steering via reinforcement learning with some successful trajectories of FRS. And this becomes the prior experience or the prior for the RL search. And then, but they also add some auxiliary loss so that it keeps in the distribution of the FRS. Yeah, and why this helps is, as mentioned, this biases the exploration towards more useful behaviors. And I think the key takeaway here that I will skip some of the very small details, but the key here is by combining this RL with this flow reversal steering, this is the most sample efficient method compared to maybe standard RL or maybe some residual RL or some other methods using reward models. And even on the harder tasks, for example, naively using steering via reinforcement learning actually plateaus because the base policy is already very weak. But when you use FRS, it actually is able to find very early successes and then converge much faster. So yeah, some of the real world experience validate what we already discussed in summation, which is that FRS is able to transport real robots and is able to boost performance from just a very small amount of human steering or human rollouts, for example. And you can also, yeah, as mentioned here, you can also learn from just offline demos, not online steering needed. So as mentioned here, as shown here, you can actually see that the offline demo method, it can actually outperform both the base policy and also standard behavior cloning with offline data. So yeah, I think this is the summary where FRS is a method to map course reference actions into flow policies noise via what is called reversal. And this shows that by using this kind of flow reversal, you can get zero-shot steering. You can also get fast noise-based BC and also bootstrapping for RL. And there are some limitations, for example, that is as usual with steering is that it very depends on the prior. So that means the generalist also still needs to be quite good in general. And I think the guidance quality also matters. So the course action that is produced also needs to be somewhat have some quality. So this is also where it can be improved. And right now, I think it's also only local steering, which means it's local to samples of actions, and it's not very long horizon or full planning. So I think in the future, these are some future work that can be tackled for this paper. So I think that summarizes the presentation. And yeah, thank you for listening. And if you have any questions or comments, please feel free to let me know.
Thank you for our presentations. Let's move on to the Q&A sessions. Are there any questions or comments from the audience?
I think I am in charge of that part. So first of all, thank you for your presentation, and I hope you're doing well in Ithaca.
Yes.
Okay. Okay, sounds good. I have a question about the fundamentals of this proposal, like the flow reversal steering part.
Yep.
Yeah, I think that figure would be good. In my understanding, so first you get the rough action from either human or VLM, right?
Yes.
And then you do the slow reversal to try to get the ground truth noise.
Yeah.
And then you do denoising from that noise so that the final action will be close to the rough action, but it's still sampled from the VLA. So it's in distribution. Is it correct?
Exactly.
In the
Yes,
first
that's exactly it.
Okay. And my question is, because in my understanding, flow matching defines the ODE, which is deterministic. So I was wondering why the final action is exactly the same as the rough action.
I see. That's a good question. So I think there's some math in the paper that I didn't mention here because it's a bit difficult to put in, but they do make some modifications to the ODE. For example, the ODE is defined backwards, for example, in time. So they use some kind of Euler integrations to kind of modify the ODE so that essentially what they want is that they want its actions to be reconstructed similarly to the distribution, but not identical, as you mentioned. Like it doesn't map it back again to the reference action, right? So there is some math in there that they modify from the original flow matching, I think.
Okay.
But yeah, I didn't put it here exactly in the presentation. Yep.
Okay, thank you. I'll check the paper.
Yep.
Sorry, maybe it's just a confirmation question.
Yep.
But
yes.
Related to the Kamijo-san's question, so my understanding is that the noise estimated at the second phase is not the ground truth information, right? And it's actually just a difference. The noise from estimated from the noise, difference action. And so it is, I think it's okay to, I'll say, even it is deterministic. So
I see.
in my understanding. And maybe it's related to the last slide. Maybe so. Maybe I'm going to move on the elevator, so maybe my connection will be better. Could you please go to the last slide? So, as the paper mentioned,
岩沢さんなんかまた出なきゃいけないみたいな、ごめんなさい。
そうですね。ちょっと時間がはい、もうちょっと過ぎちゃってしまったんで、これで QA セッションを終わりたいと思います。
はい、ありがとうございます。
はい。I'd like to conclude this session. Thank you very much.
Thank you.